Hello my dear students, in this lecture we will learn about Laplace transform and its properties and its application in the system, continuous time system, linear time systems, LTI systems. So first of all, it's the bilateral thing, Laplace transformation. The bilateral or Laplace transform of the function x denoted as like this. You can see there is L shape to consider the Laplace transform of x, or after transformation we can write it like the capital of x, capital X, and is defined as that xs is integrated with minus infinity to plus infinity with xt e to the power minus st dt. That means in Laplace transformation we convert the system, the time domain system, to its frequency domain system, but here is the factor. You can say that this is quite similar to the Fourier series or Fourier transform. In some occasions it's similar, but the Laplace transformation is not only make the time domain to the frequency domain, but it's not dependent on the angular frequency. It is mainly dependent on the s. It means, as you know, that is the as we know the complex variable. You probably know that is x axis there is a sigma, and y axis there is a j omega. So that is an s plane around it. So these planes are complex planes, known as the complex planes. S plane. That's not the just like you can say uh, that's not the similar of the Fourier transforms. In Fourier transform, um, here you can see that is x omega. That means in Fourier transform the time domain is transferred from time domain transform to the frequency domain, and the notation under the x was omega, that means angular frequency. But here we can see that the time domain has been transferred in the s plane. Okay, s plane. S plane means complex plane. Okay, and the inverse transformation is quite similar. These equations are quite similar because you just have to put the function here, x of t is the function, and just multiply with e to the power s minus st. Whenever you would use the Fourier transform, you use minus j omega t, and whenever you use the Laplace transform, that is s minus s, and s is equal to j omega, s is equal to j omega, and that is s is equals to sigma plus j omega. It's a complex value. When the sigma is 0, that there is no real value in s plane, then it is transformed into the Fourier transform. So there is a relationship between Fourier transform and Laplace transform, but the equation are quite similar, quite same. The inverse Laplace transform of x is denoted like L inverse. This is very artistically drawn, L. Just like that, you can draw like this. It's L. You make it inverse, so it's inverse. L of x is equal to x. Then the similar to the previous one, xt, but similar to the previous means I would like to say that the Fourier transform. Xs in the s plane transformed, and e to the power st, the minus will now be plus st. ds, that means the integration will occur in the s plane, and the range is minus j infinity to the plus j infinity, and sigma is quite similar to both, but here is, you can see, 1 by twice by j. But if you look upon the previous Fourier transforms, you can find it 1 by twice by. Here there is no j here, where the real part of the s value is the sigma. As I have said before, the s plane is a complex plane, and sigma is the real part. So if you want to find out the real of s, that will be the sigma, and is in the ROC of x. ROC means the region of convergence, and that is very much popular in jet transform that that's related to jet transform. In jet transform, that is, if you just convert s as a jet, because because here we can see that sigma plus j omega, it's a complex value. So jet transform are considered as the complex plane. So that is quite similar to it. In the ROC of x, note that this is a contour integration, since x is complex. S is a complex value, and that is a contour integration. The ROC means the region of convergence, and we refer to x and capital X as a Laplace transform pair, and denote this relationship as xt. If you make it the Laplace transform, you get the xs. That means the time domain has been replaced with the uh, complex domain. In practice, we do not usually compute the inverse Laplace transform by directly using the formula from above. Instead, we resort to other means to be discussed later. Now, the main part is that while you are using the bilateral or unilateral Laplace transform, so there are two types of Laplace transforms. First is the bilateral Laplace transform, that means it's two-sided Laplace transform. Second is the unilateral Laplace transform, that means it's one-sided Laplace transform. The unilateral Laplace transform is most frequently used to solve systems of linear differential equations with non-zero initial conditions. And as it turns out, the only difference between the definitions of bilateral and unilateral Laplace transform is the lower limit integration. In the bilateral case, the lower limit is minus infinity, whereas the unilateral case, the lower limit is 0. That means, just look back upon to the equation. If that is 0 to infinity, that is unilateral. If that is remains minus infinity to plus infinity, that is bilateral. That means two-sided. For the most part, we will focus our attention primarily on the bilateral Laplace transform, that means minus infinity to plus infinity. And we will, however, briefly introduce the unilateral Laplace transform as a tool for solving differential equations. That means whenever we will solve the differential equations, we will call back the unilateral Laplace transform. That means the limit will be 0 to plus infinity. And unless otherwise noted, all subsequent references to the Laplace transform should be understood to mean bilateral Laplace transform. Now, the main factor is the relationship between Laplace and Fourier transforms that I have said you in the early of the video. In beginning of the video, I have told you that what is the relationship between these two. That if you replace s as j omega, you will definitely get the Fourier transform, where omega is the real, but as you know, that is j means the complex number, real set except omega, that is this. Due to the preceding relationship, the Fourier transform of x is sometimes written as x j omega. The function x is evaluated at an arbitrary complex value s equal to sigma plus j omega, where sigma is equal to real part of s and omega is imaginary part of s. So we can also be expressed in terms of Fourier transform involving x. In particular, we have this. So that is quite similar. Just if you put the s as j omega and make sigma as 0, so it will relatively compared to the Fourier transform. And now we are heading towards the next part. That means that's the end of the video. Now you can see that is the relationship between the Laplace and Fourier transform. All about we know about it. That is the basic of the Laplace transforms. Thank you very much for being with me.